Welcome to Unit 33. We look at calculus and music. A music piece is just a function. So we play something for a time t. That's nothing else than a function. And in Mathematica you can say play instead of plot, and it will play the sound. And this function here is the amplitude. And this is time. And what the computer does is it samples the function at lots of points. So, of course, there are only finitely many data, and usually what you have in this framework is like 44,100 samples per second. If you record for 1 second, you have 44,100 points. And you can see this function. If you record something here, I make a recording. So I can now play this function. I make a recording. And you see here the function, the amplitude of the sound. We will talk about the Holland wave function just in a second. How do we get the function back if we have the data, this interpolation data? And the answer is given by the Whittaker-Shannon interpolation formula. We have already seen Claude Shannon, who just lived very close, about a mile or two from here. And so the formula involves the sinc function, this beautiful sinc function. So what we have f of t is the sum, and we sum over all data points, and then we take the f of k, and then we take the sinc of t minus k. So this is the interpolation formula, and I remind you about the sinc function. So that is sinus x over x, and especially sinc of 1, sinc of 0 was equal to 1. That was an important thing, that fundamental theorem of trigonometry. See how important this function is here in this framework. Is that it appears here, and you see if t is equal to k, we don't want to have a problem. So that's absolutely no problem. This function is perfectly fine at x equal to 0. Okay, let's look again at this function which we have seen here. This function here is not really the function, because what happens is that the frequency is 440 Hertz. This means the function goes in 1 second 440 times up and down. We don't even see that here in this, cannot see that in this graph. Here it goes maybe about 10 times up and down. So what we have is the following situation. So the function itself oscillates very, very, very fast. Amplitude, the connections of all these maxima, that's what we call the hull. I actually want to call this just h of t. And then there is also a waveform which comes in, which tells you how it sounds. Kind of that's the kind of instrument which you're using. So what you have is f of t is typically like a hull, and then we have a g of, maybe if it's 440 Hertz, it would be 440 times 2 pi t, where g is the waveform. That's the hull. So waveforms can be in different ways. You can, for example, have the sine function, you have the sawtooth function, or you have the function which is this rectangular waveform here. So these are all possible waveforms. Of course, that's quite boring. If I sound here, that's a sine which is quite boring. If you look at real applications which have kind of like here, GarageBand is one of the things. What you have is, what you can play is, you can play different instruments. For example, you can And so what we have is we have used a different waveform than here. We just actually changed the instrument to maybe something else. So that changes the G. That's kind of the instrument. That's the amplitude, kind of tell you how loud it is. And that's the frequency. So these are the three things, right? We have the type of instrument which you have. We have the hull, which you can see. And let me just take an example. Right? If we take, for example, if we take sinus 3t times sinus 1000, 10,000 t, that would be a function which looks something like that. So it has just a sinus 3t. So this sinus. And so what actually then happens, the actual function here. Okay, let's look again at the piano. So what we have in a piano is 12 tones. And what happens is, this is a very interesting thing, what happens, the frequency gets multiplied by the 12th root of 2 each time. There is also this is best explained by looking at what we call the Midi function, a function which is involving a frequency and then telling that every time we go one step up, we change the frequency by the 12th root of 2. So what we have is f of s. So this is the Midi number. So the Midi number is equal to 440 Hertz times 2 to the, and then what we have is a s minus, and it's here 29. So that's the thing over 12. So we start with s equal to 0 is 29, and this is the frequency. And the Midi number is something like telling which tone we have. So every tone in the piano has a specific Midi number, or an instrument has a specific Midi number. And I like this also to mention in this lecture, because what we have here, a natural way, we have a natural place where the exponential function comes in. So let's look at that. Let's remind you here what that actually means. So what we have is we can rewrite that also using the exponential function. So that's 440 times e to the s minus 29 over 12 times log 2. Now, if we hear a sound, we want to find what the Midi number is, we have to invert that function. So the inverse function gives us s. So s, if we want to solve for s, if f is given, that gives us this exponent. So we have the log of this. If we take the log of this, then we get this expression here. Now we have to take this expression, multiply by 12 over square root of 2. And then at the very end, that we have now s minus 29, we add 29. So that's the Midi number, depending on the frequency. For every frequency which we have, we can assign a Midi number. Of course, we want this to be an integer. And you can ask yourself, why do we take this, 12 tone thing? So that 12 tone, you can also change that. And there are other cultures who use more frequencies. So for example, I can say, I want the Japanese scale, a Japanese scale. The 12th root of 2 is really kind of a nice mathematical way. And the reason why we like this 12th root of 2, why do we like the 12th square root of 2? It turns out the 12th square root of 2, if you look at all the powers, they are close to rational numbers. And the rational numbers were originally used for frequencies. Like the Pythagoreans liked rational numbers because the fractions, the basic fractions, appear in music. So what one has is fractions as frequency fractions. For example, 2 to 1 That's an octave. 4 to 3. Perfect. I think it's called the perfect fourth, etc. So you have fractions, and so 4 to 3. So that's n over m. That's a fraction. And you are interested which fractions sound good. That's an octave. That sounds good. Also, that sounds good. That sounds also a little bit less. What doesn't sound good is this. Start to like it when you listen to jazz, for example. And Euler, what Euler did is Leonhard Euler kind of devised a way to measure the sweetness of a fraction. And I always assume that this fraction is already reduced, right? There's no common denominator here. So it's not 8 over 6, we would write 4 over 3. And what Euler defined is this n over m, he defined it as 1 plus the sum over all prime factors which appear when you take n times m, and then you take p minus 1. So, for example, when you take, maybe we take 4 over 3, so e 4 over 3. So this is 1 plus the sum over all primes which divide 3 times 4, 12, p minus 1, so that's 1. So which primes appear here? So what we do is we write 12 as 2 times 2 times 3, so these are the primes, and plus, so we have 2 minus 1 plus 2 minus 1 plus 3 minus 1. So that's 1 plus 1 plus 1 is 3 plus 2 is 5. This Gradus Suavitatis, that's kind of the nice name which Euler, Gradus Suavitatis. Pleasure is suavis, sweet, and suavis is sweet, and gradus is a degree of sweetness.